In a 480/277 volt three-phase system, a neutral conductor is indeed required from the disconnect to the panel, and a grounding electrode conductor, or GEC, should not be used in its place. The reasoning for this is rooted in the fundamental principles of electrical distribution and safety. Even when the utilization voltage is exclusively 480 volts for equipment, the neutral conductor plays a critical role. The neutral conductor serves as the return path for unbalanced current within the three-phase system. In a perfectly balanced three-phase system, the current in each phase is equal, and the neutral conductor would ideally carry no current. However, in reality, loads are rarely perfectly balanced. This imbalance creates a net current that flows back to the source through the neutral conductor. Firstly, consider that while 480 volts might be used for primary equipment, it is highly probable that a transformer will be installed to derive 120 volts or 208/120 volts for lighting and receptacle circuits. These single-phase circuits require a neutral conductor to complete the circuit and allow current to flow. Without a properly sized and installed neutral conductor, these circuits would not function correctly, and the electrical system would be incomplete and potentially unsafe. Secondly, the National Electrical Code, or NEC, mandates the presence of a neutral conductor in systems where it is used as a circuit conductor. The NEC provides specific guidelines for sizing and installing neutral conductors to ensure that they can safely carry the anticipated unbalanced load. Ignoring this requirement is a violation of the code and can lead to serious consequences, including electrical fires and equipment damage. The difference between a GEC and a neutral conductor is crucial to understand. A GEC connects the electrical system to the earth, typically through a grounding electrode such as a ground rod or a metal water pipe. Its primary purpose is to provide a low impedance path for fault currents to return to ground, which helps to trip circuit breakers or fuses and clear ground faults quickly. A neutral conductor, on the other hand, is a current-carrying conductor that provides a return path for the normal flow of current in a circuit. It is part of the electrical circuit itself and is essential for the proper functioning of the system. The GEC is not intended to carry continuous current under normal operating conditions. It only carries current during a ground fault. The neutral conductor, however, is designed to carry continuous current as part of the normal circuit operation. Thirdly, in the scenario described, the neutral conductor is already providing a return path for current flow, making a separate GEC redundant. The NEC allows for the neutral conductor to be grounded at the service entrance, which establishes a connection to the earth. This grounding ensures that the electrical system is properly referenced to ground and that fault currents can flow back to the source. If the neutral conductor is properly grounded, a separate GEC is not necessary for this purpose. However, it is important to note that the grounding of the neutral conductor must be done in accordance with the NEC requirements. The grounding electrode must be of the correct size and type, and it must be properly connected to the neutral conductor. Fourthly, a statement that only 480 volts will be used for equipment is not a sufficient reason to omit the neutral conductor. Even if all the equipment operates at 480 volts, the neutral conductor is still necessary for the lighting and receptacle circuits that will be powered by the transformer. These circuits are essential for the safe and efficient operation of the building, and they cannot function without a neutral conductor. Ignoring this fact is a serious oversight that can have significant consequences. To further elaborate, consider the specific requirements for sizing the neutral conductor. The NEC provides detailed guidelines for calculating the neutral load based on the type and amount of connected loads. These guidelines take into account the potential for imbalanced current and ensure that the neutral conductor is adequately sized to handle the anticipated load. In some cases, the neutral conductor may need to be larger than the phase conductors, especially if there are significant nonlinear loads such as electronic equipment that generate harmonic currents. Harmonic currents can cause the neutral conductor to overheat if it is not properly sized. Therefore, it is essential to carefully calculate the neutral load and select a conductor size that is appropriate for the application. Moreover, the installation of the neutral conductor must be done in accordance with the NEC requirements. The conductor must be properly supported and protected from physical damage, and it must be connected to the neutral busbar in the panel board using approved connectors. The neutral busbar must be properly grounded to the grounding electrode system. All of these requirements are designed to ensure that the neutral conductor functions safely and reliably. In addition to the technical considerations, there are also important safety considerations. A properly installed neutral conductor helps to reduce the risk of electric shock by providing a low impedance path for fault currents to return to ground. This allows circuit breakers and fuses to trip quickly, which can prevent serious injury or death. Omitting the neutral conductor can increase the risk of electric shock and create a dangerous situation. Therefore, it is essential to follow the NEC requirements and ensure that the neutral conductor is properly installed. To summarize, in a 480/277 volt three-phase system, a neutral conductor is required from the disconnect to the panel, even if only 480 volts is being used for equipment. The neutral conductor serves as the return path for unbalanced current and is essential for the proper functioning of lighting and receptacle circuits. A GC is not a substitute for the neutral conductor and is only necessary if the neutral conductor is not present. The NEC provides detailed guidelines for sizing and installing neutral conductors, and these guidelines must be followed to ensure the safety and reliability of the electrical system. Understanding the purpose of the neutral conductor and following the NEC requirements is essential for any electrician or electrical contractor working on a 480/277 volt three-phase system. It is important to take the time to properly design and install the neutral conductor to ensure the safety and reliability of the electrical system. By adhering to these principles, one can avoid potential problems and ensure the safe and efficient operation of the electrical system. Furthermore, it is important to consider the long-term implications of omitting the neutral conductor. While it may seem like a cost-saving measure in the short term, it can lead to significant problems in the future. For example, if the building is ever expanded or renovated and additional lighting or receptacle circuits are added, the lack of a neutral conductor can make it difficult or impossible to properly connect these circuits. This can lead to costly and time-consuming rework. In addition, omitting the neutral conductor can make it more difficult to troubleshoot electrical problems. If a fault occurs in the system, it may be harder to trace the source of the problem without a properly installed neutral conductor. This can lead to prolonged downtime and increased maintenance costs. Therefore, it is important to take a long-term view and consider the potential consequences of omitting the neutral conductor. In most cases, the cost of installing a neutral conductor is relatively small compared to the potential costs of not having one. It is always better to err on the side of caution and ensure that the electrical system is properly designed and installed. In conclusion, the neutral conductor is an essential component of a 480/277 volt three-phase system. It serves as the return path for unbalanced current, provides a path for fault currents to return to ground, and is necessary for the proper functioning of lighting and receptacle circuits. Omitting the neutral conductor can lead to serious consequences, including electrical fires, equipment damage, and increased risk of electric shock. Therefore, it is essential to follow the NEC requirements and ensure that the neutral conductor is properly installed. The distinction between a neutral conductor and a grounding electrode conductor must be clear. They serve different purposes, and one cannot substitute for the other. The neutral carries current under normal operating conditions, while the GEC provides a path for fault current. The code mandates the use of a neutral in systems like the one described for a reason, and ignoring this requirement is not only a code violation but also a potential safety hazard. Always consult the NEC and qualified electrical professionals for specific guidance on electrical installations. Safety and code compliance should always be the top priorities. Remember, a well-designed and properly installed electrical system is essential for the safety and reliability of any building or facility. Taking the time to do it right is always worth the effort. Let's consider the specific NEC articles that address the requirements for neutral conductors in 480/277 volt systems. While I cannot provide the exact wording of the code, I can outline the relevant sections and their key points. Firstly, Article 250 of the NEC covers grounding and bonding. This article provides the general requirements for grounding electrical systems, including the grounding of the neutral conductor. It specifies the types of grounding electrodes that are permitted and the methods for connecting them to the electrical system. Secondly, Article 220 of the NEC covers branch circuit, feeder, and service calculations. This article provides the guidelines for calculating the neutral load and determining the appropriate size for the neutral conductor. It takes into account the potential for unbalanced current and the presence of nonlinear loads. Thirdly, Article 310 of the NEC covers conductors for general wiring. This article provides the requirements for selecting and installing conductors, including the neutral conductor. It specifies the ampacity of conductors and the conditions under which they can be derated. In addition to these general articles, there may be other articles that are relevant to specific applications. For example, if the 480/277 volt system is being used to supply a data center, there may be additional requirements for grounding and bonding. It is important to consult all applicable NEC articles and to understand the specific requirements for the application. The NEC is a complex and comprehensive document, and it is essential to have a thorough understanding of its requirements before designing or installing any electrical system. Consulting with a qualified electrical professional is always a good idea. Moreover, it is important to stay up to date on the latest edition of the NEC. The NEC is updated every 3 years, and the new editions may contain significant changes that affect the design and installation of electrical systems. Staying informed about these changes is essential for ensuring that electrical installations are safe and compliant with the latest codes. There are many resources available for learning about the NEC, including training courses, seminars, and online forums. Taking advantage of these resources can help electricians and electrical contractors stay up to date on the latest codes and best practices. In addition to the NEC, there may be other local codes and regulations that apply to electrical installations. It is important to check with local authorities to determine what codes and regulations are in effect in the area. Local codes may be more stringent than the NEC, and it is important to comply with all applicable requirements. By following the NEC and local codes, one can ensure that electrical installations are safe, reliable, and compliant with all applicable regulations. This is essential for protecting people and property from the hazards of electricity. Let's delve a bit deeper into the practical implications of neglecting the neutral conductor in a 480/277 volt system. Consider a scenario where, despite the code requirements and best practices, a contractor decides to run only the 3-phase wires and the GEC to a sub-panel intended for future lighting and receptacle circuits powered by a step-down transformer. Several potential problems could arise. Firstly, without a dedicated neutral conductor, the voltage balance in the downstream single-phase circuits derived from the transformer could be severely compromised. Single-phase loads connected to different phases of the transformer would experience voltage fluctuations and imbalances, potentially damaging sensitive electronic equipment. Secondly, the reliance on the GEC as a return path for normal circuit current is a fundamental violation of electrical safety principles. GEC are designed to carry fault current only, and they are typically sized much smaller than neutral conductors. Overloading the GEC with continuous circuit current can cause it to overheat, creating a fire hazard and compromising the effectiveness of the grounding system. Thirdly, any ground fault that occurs in the downstream single-phase circuits would have a limited and potentially high impedance path to return to the source. This can prevent overcurrent protection devices like circuit breakers from tripping quickly, increasing the risk of electric shock and equipment damage. Fourthly, troubleshooting electrical problems in such a system would be significantly more difficult. Without a properly defined neutral conductor, it would be challenging to isolate faults and determine the cause of malfunction. This can lead to prolonged downtime and increased maintenance costs. Fifthly, the lack of a neutral conductor can also create problems with harmonic currents. Nonlinear loads, such as electronic equipment and LED lighting, generate harmonic currents that can circulate in the neutral conductor. Without a properly sized neutral conductor, these harmonic currents can cause overheating and voltage distortion. Sixthly, the cost of retrofitting a neutral conductor to the submill after the initial installation would likely be significantly higher than including it in the original design. This can involve running new conduit, pulling new wires, and making modifications to the panel board. Therefore, it is always more cost-effective to include the neutral conductor in the original installation. To avoid these potential problems, it is essential to follow the NEC requirements and best practices for installing neutral conductors in 480/277 volt systems. This includes properly sizing the neutral conductor, grounding it at the service entrance, and protecting it from physical damage. By taking these steps, one can ensure the safety, reliability, and performance of the electrical system. It is crucial to remember that electrical systems are complex and unforgiving. Even small errors can have significant consequences. Therefore, it is always best to err on the side of caution and to consult with qualified electrical professionals when designing or installing electrical systems. Their expertise and experience can help to prevent costly mistakes and ensure the safety of people and property. And remember that following a qualified professional is essential for the safety of the system.